Okay, good. I said analysis, I should have said analytics. We train machine learning models so that they learn relationships in the data. The expectation is that these learned relationships are true and by extension fair. But what if the data is biased? Or the data is accurate, but the truth is biased? Wouldn't we want to understand and correct these biases? Hello, everyone, and thanks for joining us. My name is Ali Sharif, and I'm a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Serge Massis. Serge has been at the confluence of the internet, application development, and analytics for the last 2 decades. Currently, he's a climate data scientist at Syngenta, a leading agribusiness company with the mission to improve global food security. Previously, he co-founded a search engine startup incubated by the Harvard Innovation Labs that combined the power of cloud computing and machine learning with the principles in decision-making science to expose users to new places and events efficiently. Whether it pertains to leisure activities, plant diseases, or customer lifetime value, Serge is passionate about providing the often missing link between data and decision making, and machine learning interpretation helps bridge this gap more robustly. Serge is also the author of the Interpretable Machine Learning with Python book that is scheduled to be released in April by the UK-based publisher Pact, and we are very lucky to have him. Serge will be presenting explainable AI with monotonic interaction constraints, and cost-sensitive learning. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn the presentation over to Serge. Please take it away.
Hi, guys. Thank you for joining. Thank you, Ali, for your great introduction. Without further ado, I'll be, talking about the outline of this presentation. It has two parts. The first underpins the importance and necessity of using guardrails in machine learning, and particular when and why to use monotonic and interaction constraints. The second uses an example with merit-based scholarships to explain how three methods can be leveraged to make a model fair with LightGBM model, and we will briefly discuss a deep learning approach as well. So, okay, this is just a quick introduction of why we need to place guardrails to begin with. AI's promise and potential, if you will, its value proposition is to make better decisions than humans, or to help us make better decisions. It shouldn't be too hard. We make crappy decisions. However, we are accountable for them, and we can tell people our reasons, show doubt, and even change our mind. Algorithmic decision-making is held to higher standards because they're taken at face value. So how can we trust machine learning model to fulfill this promise? Trusting the model is rarely about the model. Let me repeat that. Trusting the model is rarely about the model. Here we have a simple diagram of supervised learning. Supervised learning has a fundamental flaw, which is it depends on data, often produced by humans or our machines. And this data can be flawed in many ways. But worst of all, what if your data truly doesn't represent the environment your model intends to generalize? If that's the case, the domain knowledge won't align with what you observe in the data. What if the environment that produced the data has built-in or systemic or institutional biases? Then the data will reflect these biases. These are the ugly truths. And in addition to that, we have the fake and changing truths, complicating things even further. In data science, there's a mantra to trust the data, to let it do the talking. But given all the baggage data comes with, how can we? Models cannot make better decisions than humans as long as bias is in the way. To this end, we need to step in and ensure that guardrails are in place. Indeed, how can we trust the model more? We have things we can do to the data and others to the model. Complexity is one of the biggest enemies of interpretability because with so much noise, it's hard to hear the signal. We can reduce the amount of features in the dataset or introduce regularization to this end. Also, even if the data is relevant to the model might learn the wrong things from it. This is why you need to place some guardrails to help point it in that right direction. This can be achieved by creating features that capture the noisy interactions going on in your data and placing monotonic constraints so that independent and dependent variable relations always go in one direction. Bias is an issue not only in the data side, but when precision is more important than recall or vice versa. This is when cost-sensitive learning can help align your predictions to your mission, be it safety or fairness. Lastly, you want reliable predictions that can withstand unexpected scenarios, be it from natural anomalies or from coordinated adversarial attacks, and to ensure privacy when needed. Incidentally, there's also a third column for inference, but we won't discuss it here. In this session, we'll only focus on these methods. So let's dig in. So in this session, we'll cover two kinds of constraints, monotonic and interaction. Let's first explain how and when monotonic constraints are useful. So data can be messy, so rules cannot be applied consistently. For instance, here we have some critical recidivism data. Let's say we know that defendants have priors, for defendants, priors per years tend to decrease with age. This is supported by our criminological domain knowledge. However, data is sparse for older age groups, while there are a number of high leverage outliers that contradict the domain knowledge, showing a few peaks in the function, as you can see here, and even here at the end. Monotonic constraints forces a model to comply with the domain knowledge that priors per years decreases monotonically with age. Sparsity is also a problem when you have underrepresented groups in the categorical features. Often when a group is underrepresented, the lack of data for one group versus the other will create more opportunities for the model to learn inconsistent and therefore unfair relationships between features and the outcome. This could end up privileging or underprivileging these groups because models will learn double standards. Say gender 1 is very underrepresented in a way that the model learns that priors per year only increases slightly as age increases. But gender 2 does support the domain knowledge hypothesis, which says otherwise. Monotonic constraints, sorry about that. Monotonic constraints ensure that relationship is consistent, which makes it fair. Note that this doesn't make the outcome equal, but it's a good start. Another problem is what happens when you apply the model to unseen data, as you would expect to. What happens if data has ages outside of the bounds of training feature range? Let's say we train the data only in the bounds of 18 to 68. A non-monotonic model will not have a consistent relationship between age and priors per year, but a monotonic model will continue on trends. Incidentally, this model is for adult defendants, so we're only interested how a model will perform for people older than 68. But with many models, it's a concern what happens when you push the boundaries on both ends. So to sum things up, why use monotonic constraints? Because they can enhance models by ensuring fairness, consistency, and reliability. What about interaction constraints? Likewise, we have similar issues with the interactions between features, which can be counterintuitive, contradicting domain knowledge or adding bias to the model. So we can identify them and remove them through interaction constraints. For example, this is a heat map of interaction values measuring the strength of relationship between any two features. We can identify problematic interactions. For instance, it's well known that juvenile delinquency features correlate highly with growing up in a rough neighborhood, which unfortunately correlates with race. But we should not let these features interact with the adult priors nor age group, which could be unfair. We may need then decide to constrain the model in such a way which these interactions are removed. So as you see here, the parts in red were essentially zeroed out. So now we begin with part 2, which is about fairness, for a merit-based scholarship example. The code example of this presentation is about merit-based scholarships. A law school wants to develop a model to help decide which students are most worthy of a scholarship. For those that don't know, a bar exam is an exam that a law graduate takes to qualify to practice law. The premise is that law students that are deemed most probable of passing the bar exam are most worthy of a scholarship. So in predictive analytics, this is what we're usually faced with, which some kind of truth that is captured by the data, which the model learns from, and then makes a prediction with it. Even though we measure the prediction against the data, we always hope that the prediction is not far from the truth. However, there's a series of assumptions pertaining the truth, data, and model that intensify predictive bias. For instance, is society fair, and does the data accurately depict it, and can the model even fairly represent it? These are all valid questions. The data set the law school wants to train with is a data set with nearly 23,000 law schools that over the years have taken the bar exam. They want to use the resulting model with their own students to determine scholarship eligibility. Please note that approximately 95% of all law graduates eventually pass the bar exam. So it's a completely unbalanced classification problem. In addition to some demographic and academic details, the dataset has 2 features related with grades. It's the first 2 features. And to comply with social meritocratic norms, they want to ensure that those with the highest grades have the higher likelihood of passing the bar and therefore getting a scholarship. However, there's a problem. The issue with the grade features is that they're unevenly distributed. As you can see here, they're mostly, fairly, middle of the ground grades, and there's some with high grades, but there's not, a lot on the tails of these 2 distributions for LSAT and undergraduate GPA. And you also see differences, as you would expect, between those that passed the bar exam and those that failed the bar exam. This unevenness leads to uneven distribution of probabilities of passing the bar within the data Excel. Look at how the counterpart of those with the highest probability are in the corner with the highest grades, and those with the lowest probability are in the opposite corner. However, it's by no means smooth progression between corners. For example, take a look at the highlighted area with the high probability of passing the bar is connected to a low LSAT score and a mediocre undergraduate GPA. So how is it possible that these 2 would lead to, a higher probability of passing the bar? Well, in reality, that has to do just simply because as I said, there's a sparse area with some outliers. So the first method we will discuss is cost-sensitive learning. Unbalanced classification problems due to the uneven representation of classes are tricky in data science, no doubt. And there are many ways to deal with them. Some pertain to data, others the model. This method involves the model. And how it works is by penalizing one type of misclassification more over than the other in the loss function. So using cost-sensitive training, we will now train a light GBN classifier. This is how you would train this classifier with no cost-sensitive training. It's just very simple. You initialize the classifier and then you fit it. With one small change, we can make it cost-sensitive. Notice the yellow highlighted area. This parameter controls class weighting, which is one of the many ways you can incorporate cost-sensitive training. It essentially means that your misclassifications on the majority class are worth 1/5 of the minority class. You can set this number to begin with as a ratio between positive or negative classes, but the optimal number is obtained by hyperparameter tuning. In this case, we use the highest Matthews correlation coefficient, which measures balance between all quadrants of the confusion matrix. Speaking of the confusion matrix, without class weighting, you get this confusion matrix. It has an accuracy of nearly 95%, but misclassifications are far more common with not passing the bar than passing the bar. Fairness cannot be addressed if there's such a large imbalance between misclassifications. So this is essentially what you get without cost-sensitive training, and with cost-sensitive training you get this. Sure, accuracy is 3% lower, but notice how much more true negatives were captured. This is on the top left corner versus this on the top left corner. The trick in achieving this balance was to maximize on the mask use correlation coefficient, which you can tell is highest on the right side than it is on the left side. It is 0.26% on one side and 0.6 on the other. So to understand the outcomes of the model, we will use SHAP, which is an interpretation library derived from game theory. So it has some mathematical principles that make it reliable. It has many explainers used for different scenarios. This is a tree ensemble, so we will use tree explainer. A SHAP explainer produces SHAP values, which you can plot in many ways. One way is through a summary dot plot. Most important features are at the top and least important towards the bottom. Each dot for each feature is an observation. The color of the dot represents the value of the feature, and its position to the left or the right of the line represents the impact or the outcome. So this is how they positively correlate versus negatively correlate, and these dots represent that. So you can tell, for instance, that the higher grades for the LSAT and the undergraduate GPA correlate with the passing the bar, but the color coding isn't consistent, so it isn't exactly monotonic. Also, not surprisingly, higher family incomes do too. Another neat insight is how even though binary features that denote full-time and part-time, so you can see here, full-time and part-time students are nearly opposite to each other. The model picked up on this redundancy and made part-time irrelevant, because as you can see, the dots aren't on either side. You know, they're mostly in the middle. Another thing SHAP can derive, but only from tree ensemble models, is SHAP interaction values. With this, we can plot a heat map with averages of the absolute values and place zeros on the diagonals to only observe the interactions. The stronger interactions are between the grade features, which makes sense, but there's some counterintuitive interactions between other features and the grade features in red. So that's what we have to wonder. Why should family income correlate with the grades? We shouldn't let it interact with the grades at all. So now we're going to explain how to apply monotonic constraints to address some of these issues. So we're going to train the light GBM model with the monotonic constraints. The idea is to force the two grade features to increase monotonically with the target. This is coded as 2 1s followed by 5 zeros, as you can see here. The first 2 1s correspond to the first 2 features, which are the grade features, and they're 1 because they increase monotonically. If they decrease, they would be -0. Otherwise, they would be 0 if there was no monotonicity to be enforced at all. Okay, so now we can repeat the SHAP summary dot plot, and we can tell that the color coding is now smoother for the first 2 features, but it isn't continuous. This is because we made these highly correlated features increase monotonically, which is like forcing 2 waves to move in one direction, and there are points in which they crash against each other, and they ripple. So the rippling effect is evident here, especially in some of the sparse areas. However, it's definitely smoother in the less sparse areas. You can tell there's a more smoothness in the areas in green, for instance here, but less smoothness in the red areas. And that is completely expected given the correlation between the 2 grade features. So now we'll discuss interaction constraints. Now we can train the interaction constraint like GBM model. In addition to the monotonic constraint, we can limit interactions between only the first two features and the other 5 amongst each other. This is coded in 2 lists with the indexes of features that are allowed to interact amongst each other. So the 0 and 1 over here correspond to the first 2 features, and then these other 5 over here, the following 5, are lumped up together. We then just plug this into the initialization of the model, just as we did with the monotone constraints. As for assessing or verifying the interaction constraints, is very simple. We just compare both heap maps, and notice it's like we placed a fence around the features we wanted to interact, only allowing them to interact with other features within their group. So you only see a fence around these 2 and then another fence around these 5, and there's 0 everywhere else. That's exactly what we were expecting. So how can we implement constraints in deep learning? Well, TensorFlow Lattice has you covered. We don't get into all the technical details, but it uses interpolated lookup tables, which approximate inputs to outputs with interpolation. The mappings are produced through calibration layers, which can constrain the inputs any way we want. As you can see, there's several univariate and bivariate constraints that can be applied. The ones up here, these are univariate. We already talked about monotonicity, but there's also convexity. Like we could make it have a convex or a concave shape if we wanted to with TensorFlow Lattice. We could also make it unimodal, which means we could have it increase, decrease, and then increase as it does here, or we can have it increase and then decrease. And then as far as like the bivariate, like one of the issues you saw with the previous implementation we did with LightGBM, since you have a rippling effect when you have highly correlated features go in the same direction, and that's something these bivariate ones address by making it completely smooth. That can come at a cost of accuracy, but if you really need that kind of that relationship to hold no matter what, this is the way to go about it. You can have what is called a trust bivariate constraint, or you can have a dominance one. The only difference is dominance, one feature is more dominant than the other, but they're both calibrating 2 features to work together. So TFL layers can be included in Keras. It can get very complicated. This is an example with a book which uses Keras layers and individually input calibrated constraints and regularized. In this example, we will only implement monotonicity constraints on a canned classifier, which abstracts some of the complexity and works directly with TensorFlow rather than Keras. So there are several things to do to train a TensorFlow Lattice model. First, you will need to create individual configurations for each one of your features. To this effect, you will need 2 arrays, one describing the type of column, and another its calibration configuration. Second, you will need an input function to feed the data to the model. In this case, we're using one that leverages pandas data. Third, we will place an initialization on a configuration with the feature calibration configuration array. That's this over here. Then initialize the canned classifier with this configuration. And lastly, we will train with the input function over here. So now you can see how much smoother the contour plot is. That being said, had we used the bivariate one, it would be like a perfect gradient. But as I said, that's one of the issues you have with the sparse areas. They're always prone to this kind of issue. So if you want to check out the code from this session, you can either go to the Google Colab or clone the repository with the notebook on your desktop. I recommend the first option. Don't worry, you didn't have enough time to write down these links during the presentation. They're available in the Agrid Intellect platform. And now this is a shameless plug about my book. It's coming out about 6 weeks. It's 14 chapters. 6 weeks? No, actually, it's coming out this week. I just learned it was coming out on Friday. By the way, it's not in April, on Friday. It's 14 chapters and about 500 pages long. There's Python code and lots of visuals, but without excluding theory, which is very much needed to be able to interpret the outputs. What makes it unique is it covers both interpretation methods and solutions for interpretability issues, such as what you've seen in this session. And it's something that's not addressed in any book for practitioners so far. Also, it tackles interpretation-specific issues to deep learning and non-tabular data. I have also avoided any hello world examples, any use of toy data sets, which most data scientists have already seen 100 times and lack context, and especially lacking context. The reason for this is to use plausible, fully developed examples that have a backstory, which I call a mission. In data science, the how should never be disconnected from the why. Anyway, there's an exclusive discount for anybody that wants one. It will be active for a couple of weeks. So I'll just leave this here and move on to Q&A. So back to you.
Yeah, thank you, Serge. We will now start the Q&A part of the session, and we will be presenting Serge with live questions as well as questions we've received in advance. Mm-hmm. So maybe, Serge, the first thing is, could you just walk us through the Colab notebook and just give us a feel for what we could potentially benefit from just perusing through it?
Yeah. So everything we've seen is all here. We have the, installing the libraries, loading the libraries, preparing the data set, and then, well, it's all hidden, but everything we've seen. There's some code that's there, some utility functions, train the model. So everything we've seen is all here.
Yeah. So if a practitioner wanted to get their hands on a fully working example and see how they could potentially apply those techniques to their data set, this notebook should help them do that, right?
Yeah.
Okay.
Yeah.
Excellent.
And yeah.
Yeah. So maybe we'll go back to more high-level conceptual type questions. Now, at what point in the model development process do you start adding constraints? Do you add them in response to a problem that we identified, or do you add them up front when you identify that a protected class needs to be watched for? To tell us what your thoughts as to when do we start applying constraints to these models?
Well, I mean, if you already have some domain knowledge about your problem, I mean, you can go ahead and create the constraint from the get-go, but I would always verify the data, maybe examine it and discuss with a domain expert. Say if it didn't connect with what you knew, if there was no monotonicity, it'd be like strange. It'd be like, what's going on here? But if there was some or a large amount, and you could measure that with Spearman's correlation coefficient, you could might as well just put it. Another thing is that you find it in the data, then you validate it with someone that knows, or through other means, and you apply it. But I wouldn't apply it before examining it first. And you always apply it in the modeling stage, even if it's exploratory modeling. It's not like the final, like for production modeling.
Okay, that's useful insight. Now, I guess, Mobile, I'll curious about monotonic constraints. You've gave us examples of applying it to XGBoost and TensorFlow Lattice. Where else can we apply those monotonic constraints? Or can I, just give me a
monotonic constraints. Can be found in all tree ensemble models. They're available in CatBoost, LightGBM, iXGBoost, AutoML, and they're also available in as I said, TensorFlow Lattice, and that's about it. That's as far as I know. They're also not because they're constrained anyway, but any model that is inherently linear or monotonic will have them built in. You don't have to, put any monotonic constraints.
Yeah, so logistic regression by definition would be monotonically constrained, and therefore I would not need to impose those constraints on something like logistic regression.
Yeah.
Got it.
So,
Got it. Okay, that's very helpful. Now, can you now have you run into scenarios where you've okay? Well, I think your example you showed monotonic and interaction constraints put together. Is that correct or?
yeah.
Okay.
Yeah. Yeah,
Okay.
you can use them independently. There's no rule that, I mean, if you find a reason to constrain only the interactions, you can.
Mhm.
And if you find a reason to use monotonic constraints, you can use that. I mean, they're two independent things, and they have different use cases. I don't know if that
Okay.
answers your question.
Okay. No, it does. It does. Now, I guess when we add constraints, we're adding constraints to particular areas of the model, but so maybe one feature is monotonically constrained with the label, but the rest of the model can still do whatever it wants, right? It's still a black box. Is that correct or?
Yeah. But that's why I urge people to use feature engineering to kind of place guardrails in other places, because it's not the only thing you would want to constrain. Like you don't necessarily, monotonicity is not, like the only thing you want to constrain. Like I said, there's interactions. There might be interactions between more than one feature. There might be like things that are completely nonlinear that you want to kind of take control of. And you do that through feature engineering more than through constraints. Constraints is like something that I would do last to that, not because it's not great. It's just it's great for only controlling monotonicity, and it's still very limited. Like in TensorFlow Lattice, as I said, you can control convexity, concavity, modality. You can put constraints between two features. So, and that's something you can't do with monotonic constraints by themselves. So that's why I there's other tools to be used.
Okay. Now, okay. Thank you for that answer. Now, maybe I'll ask this question: is it possible that we can go ahead and apply monotonic interaction constraints and still end up with a biased model?
Yeah.
Okay.
But that's why there's tools for bias mitigation that
Okay.
fall outside of that realm. Like you can use reweighting, rebalancing. You can use odds calibration on the other end. Once you've already, you have two groups, one is more privileged than the other, and you can calibrate it in such a way that the underprivileged group has equal odds than the privileged group. And there's many techniques that can be used to that end. I'd say, like, even though this example was about bias, there's also domain knowledge aspect to it, which you might want to apply. There's problems even in my area of agriculture that I apply monotonic constraints. It has nothing to do with people. It has to do with plants. But I hear from like a agronomic scientist that this relationship always goes in this direction. So I apply the monotonic constraint because, as I said, even though it's not an issue to me right now, if something changes in the data, I wanted to uphold that relationship always.
Got it. Got it. Yeah, and so you're really, even though you're not observing any biases or any problems with the data that you're testing with, these are limits that you want to respect, and you want to make sure you don't end up with a model that's behaving illogically once certain bounds of the data have been exceeded.
Exactly.
Got it. Got it. Okay. Now, I guess maybe I'm just curious as to your thoughts as to fairness through unawareness. Is that if I just by what are your thoughts on having fairness maybe implemented or applied through monotonic constraints versus just hiding the features altogether?
Well, it depends.
Huh?
Like if the feature is useful, I
Mhm.
I'm not a proponent of removing it. Like there's some features that are problematic to the extent that you would want to remove them because the bias they hold. But it can be a very naive approach considering that you could have bias nonetheless in other features that carry the same information because they correlate with the feature you're removing. So you would want to do some kind of treatment to them to remove that bias. And you could do that. You can take the data, and there's a method called the disparate impact remover, and you can remove the bias from the features that aren't the feature that you want to remove. So you're essentially neutralizing that bias. And you could do that. I would propose doing that rather than removing the feature outright. Not that it might not make sense to remove the feature, but that's something that is kind of that has to be very carefully assessed, I'd say.
Yeah, so for example, if there was a feature that was race, and then we happened to remove that feature, but we kept the feature of postal code or zip code,
Yeah,
that proxy feature could just might as well get us to race anyway, because a particular neighborhood might be more weighted toward one particular race versus another.
exactly. So you
Okay.
would want to do that. I mean, and the question here is that, I mean, like a lot of these methods, you want to do all these changes and still retain a fair amount of accuracy. But when you really correct and mitigate bias, it is very possible that accuracy is going to take a hit because you're not modeling for the truth that you have, you're modeling for the truth that you want. And they're two separate things. So you want to
Got it.
improve on that.
Got it. And that's a really important point, because if there are historical biases and that led to the data to tell us one story, this technique gives us the ability to overrule those historical biases and just say, I want a future that's better than my past.
Exactly. Exactly.
Okay. Now, one could argue that if I needed to add rules to my machine learning model, then it's no longer a machine learning model. That I might as well build a
Yeah.
rule-based system from the ground up. What are your thoughts on that? And yeah, curious.
Well, I'm a proponent of using machine learning for EDA. You know, I think we can learn a lot from the models. I think it, we can work in tandem with the machine learning model and learn from them and improve on the model. And it, as I said, improving in the model is not necessarily about improving on accuracy because the data might be flawed to begin with, even the one we're using for testing. So we have to think in that sense, in that it yeah, putting the rules, because the model has nothing else to learn from the data. But humans, like it or not, have other knowledge we can capture from that the data doesn't have. The other alternative is to give the model access to that data through external data sets. So you could enhance the model by, doing all sorts of things to the data. Uh, like data augmentation schemes, like data enrichment schemes, and so forth. But at the end of the day, it's a question about not trusting the data blindly, not trusting the model blindly, being a skeptic, because it's in the word data science. Science is there. Science is all about being a skeptic, and somehow we've traded it for, like, oh, now we're all machine learning engineers, and we're throwing the science out of the equation. And I mean, so we have to have that, I mean, I'm not saying engineering is bad. We just have to have a good balance between both disciplines.
Yeah, yeah. Don't forget about the science and data science, right? That's really important.
Yeah.
That's an important message. Now, and so you do see, when I'm curious here, when you say proponent of using machine learning to in the exploratory phase. So you could potentially envision a scenario where we would develop or apply machine learning to data and just see these are the rules that it came up with, and then go back and
Yeah.
tinker with these rules and,
Yeah.
and do something different and based on what we want, not what we've done in the past.
Yeah. Like there's a very interesting paper called Automated Statistician, and there's a few others about NLG, natural language generation, which they take the model and they kind of reverse engineer some rules and tell them back to you. So you're like, okay, these are the concepts, these are like the salient relationships that we found in the data. Do they make sense or not? And I think in the future where we're using interpretation more in the machine learning workflow, we'll have all these steps where we're actually getting these notifications. We saw this. Does this make sense? Yes, yes, yes. And then it goes through this workflow that is already pre-engineered to actually come up with the best model. Because right now, AutoML is all about, okay, let's chase the best accuracy, and it just assumes everything is correct. The same with auto feature engineering. It makes it doesn't make any distinction between unintuitive and intuitive features. It just simply found a feature that produces the best outcome.
Yeah, and that's an important message to the community, because we're potentially seeing signs or at least signals of some shops going out and just say, okay, well, I have a black box model, let me just add an explanation, and voila, I'm done.
Yeah.
We have to be more thoughtful and more rigorous in our treatment of how we apply these models in high stakes decisions.
Yeah, definitely.
Okay. Now, I think that's all the questions we have here. Before we wrap up, Serge, are there any final thoughts that you would like to share with us?
No, not really. I think like I honestly think that XAI or interpretable machine learning or whatever you want to call it is the future of ML. It has to be, because as it is, it's untenable. Like the models are getting too complicated for us to truly understand, and there's so much research out there already ready to be used. So there needs to be a conduit between like the academia and everything that's going on over there and industry, where there's dire need to actually put this into use, because like the ethos right now of machine learning in practice in industry is like chasing metrics off a cliff, and that's not going to end well at all. So I really, it's the right time to be picking up on all these techniques and putting them into use.
Okay, and that's an important message, Serge, and that's probably one of the reasons I love your work. It's making a lot of these techniques accessible to practitioners, and I congratulate you on your great work with the book and with all the great presentation. So I think I'm just going to check here. I think that's all the questions we have. So Serge, I thank you for a great presentation, and I want to thank all those who joined us online. To see more free content like this, please visit our website at ai.science, a login to access the slides from this and other sessions. Also, make sure to subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.
Bye.